Let's start the lecture. In this lecture, we are going to discuss about impedance triangle. Before going through impedance triangle, you first have to go through the LCR series circuit. I already give the link in the description box. Okay. Then what is impedance triangle? In series LCR circuit phasor diagram, we have this type of diagram, is or no? Then along this direction, we have VL minus VC. Yes or no? First, just write down that one. VL minus VC. And then along this direction, we have both I and VR, yes or no? Just write down that one also. Here you can write I, here you can write VR. Okay. And then finally, along this direction, resultant direction, is our E. Then not write E here. Here you can see our EMF E lead current by phase phi. This is our current, this is our EMF. Here EMF lead. As in inductive circuit, EMF lead. Yes or no? Here we consider VL is greater than VC. So here EMF lead current by phi. Then we have to use this phasor but derive a relation among XL, XC, Z and R. That is our impedance triangle. What I write here? The relationship between the resistance. Here we have to replace VR with resistance. Okay. Then inductive reactance, in place of VL we can write XL. Capacitive reactance, in place of VC we can write XC. Then what about E? In place of E we can write impedance Z, because E is our net EMF or resultant EMF, and if we consider the reactance triangle, sorry, impedance triangle, then we have to consider Z in place of E. Here we have to write Z. Okay. Then just represent this diagram in a right angle triangle. Okay. Just see, this is our R. So let this side is our R. Okay. First just write down R. And this is O, this is A, this is B point. So here also you can write O, A, B. You can see OB is our Z, OB is our Z impedance. Okay, so no. So you have to write Z. Then this side and this side are equal. In place of FB we can also write XL minus XC. So this is our XL minus XC. Yes or no? Just write down here XL minus XC. And just see here, this is our angle phi. So this angle is our phi. Should we consider VL minus VC? That is, VL is greater than VC. To be inductive circuit. As inductive voltage drop across inductor is more than that of voltage drop across capacitor. So here we can consider as inductive circuit. Okay. So for inductive circuit, what I would write here, XL greater than XC. If XL greater than AC, then what about tan phi? From the triangle we can say that tan phi is our P upon B. This is our angle phi, then this face are perpendicular, this is our B base. So we can write B upon OA. In place of AB we can write XL minus XC upon, in place of OA we can write R. Then what about cos phi? What you have to find here? Because you know cos phi is our power factor. Okay. Just remember this one, cos phi is our power factor. This is known as power factor. Then what about cos phi? Cos phi we know b by h. B upon energy, here we have b is OA. Hypotenuse is our OB. In place of OA we can write resistance R. In place of OB we can write Z. This is for inductive circuit. Okay, as here XC is greater than AC, so you can write inductive circuit. And you can see here current lag behind the EMF. Current here, EMF is here. So current lag behind the EMF. So then if XL less than XC, then what you got here? If XL less than XC, or you can also say VL is less than VC. If VL is less than VC, then you can get a phasor in LCR just along this direction. This can becomes VC minus VL, and this is our VR. So our resultant must go through this direction, EMF E, and current is here I. So here EMF lag behind the current. So no, this is our E, this is our I. So EMF lag behind the current by phase phi, and this is the condition for capacitor. I don't know. So if XL is less than XC, so you can write capacitive circuit also. And for that we can write tan phi is our, then this becomes XC minus XL, not XL minus XC, okay? XC minus XL upon R. Cos phi becomes, as it is, cos phi becomes R upon Z. Okay. Here you can say EMF lag behind current. Okay. This is all about the impedance triangle. Then we have to go through the resonance condition. What is resonance condition? The resonance condition of a series LCR circuit. Okay. Then how do I write here? A series LCR circuit is said to be in resonance condition when current flows through it has its maximum value. When current flows through a AC circuit or series LCR circuit is maximum, then that series LCR circuit is said to be in resonance condition. What is the condition for maximum current flows through it? Maximum current means we have to minimize the impedance. Okay. If impedance decreases, then obviously current increases. Impedance means net opposition offered by the series LCR circuit. If opposition decreases, then current increases. Yes or no? Yeah. For series LCR circuit, we know I naught equal to E naught by under root R square plus XL minus XC whole square. Yes or no? For resonance condition, maximum current will flow through the series LCR circuit. That you have to minimize the impedance. Okay. For resonance condition, I naught will be maximum. When it is possible, it is possible only if XL equal to XC. You know why? Because we know R never be 0. We know what is R, what is resistance. Resistance is the opposition offered by the conductor. If conductor is there, then compulsory there is some resistance is there. So we can't neglect the resistance. But if we make the XL minus XC term 0, then our impedance becomes less, or hence we can say current will be maximum. Then what is the condition for XL minus XC equal to 0? We can write XL equal to XC. If the capacitive reactance and inductive reactance are equal, then we get XL minus XC is equal to 0. So then what about XL? We know XL is our omega L. In place of XC we can write 1 upon omega C. Then we can write omega square equal to 1 upon LC, or we can also write omega equal to 1 by under root LC. In place of omega, we can write 2 pi f also, or nu 1 by under root LC. This is our resonant frequency f, which is equal to 1 by 2 pi under root LC. For resonant frequency, we can write f as fr also, okay? Or we can also write fr equal to 1 by 2 pi under root LC. This is our required resonance frequency formula. And just remember, in series resonance, in resonance circuit, XL minus XC equal to 0. That means this, our resonance circuit behaves as pure resistive circuit, as there is no opposition by the uh, inductor and capacitor. We can say no opposition, but as the net opposition by inductor and capacitor is 0, so we can say the resonance circuit is our pure resistive circuit. Yes or no? This is all about lecture.